Welcome to this explainer. Today we're unpacking a truly unbelievable engineering mystery. We're going to look at how entirely invisible forces, things you can't even see, have the literal power to tear apart solid steel pipes. And more importantly, we'll dive into the brilliant engineering frameworks designed to stop that from happening.
Here is our roadmap for today. 1. The hidden pipe killer. 2. Defining AIV and FIV. 3. The pioneers of prevention. 4. The Energy Institute Guidelines Framework. 5. A case study on system failure. And 6. Applying the fixes.
All right, Section 1, the hidden pipe killer and the invisible forces destroying steel. You know, we usually think of heavy industrial piping as, well, virtually indestructible, right? I mean, it's thick, heavy metal. But high-capacity pressure-reducing stations hide a really dangerous secret. It honestly sounds like sci-fi, but can sound and gas flow actually destroy a solid steel pipeline in a matter of hours? Yeah, it's a terrifying reality. When you've got fluids, steam, or hydrocarbon gases blasting through at insane pressures and velocities, the internal loads create massive vibrations. And if the system isn't designed to handle it, that vibration leads to rapid metal fatigue. We're talking catastrophic failures in days or, seriously, even hours.
Section 2. Defining AIV and FIV, the two culprits.
So to solve this and stop these rapid failures, we have to identify exactly what's tearing the metal apart. And it really comes down to two totally distinct culprits. First up, AIV, or acoustic-induced vibration. This happens when devices like safety valves create immense acoustic energy. We are talking about sound so loud and intense that it vibrates the actual shell of the pipe until it fatigues and cracks, radiating this huge broadband sound between 500 and 2000 hertz. On the flip side, we have FIV, flow-induced vibration. Now, this one is highly physical. High fluid velocities cause what's called vortex shedding. Think of that chaotic swirling wake you see in the water right behind a speedboat. That violent physical turbulence batters the pipes and related systems, like tube bundles. Both are massive safety risks, but they attack the pipe in completely different ways.
Section 3. The Pioneers of Prevention. Carucci, Mueller, and Eisinger.
Now, you obviously can't fight an invisible enemy if you can't measure it. So about 35 years ago, engineers Carucci and Mueller stepped up to the plate. They desperately needed a way to predict these failures, so they looked at the raw data. They plotted 9 known pipe failures against 27 completely safe, non-failing situations. By mapping the internal acoustic power against the pipe's outside diameter, they created the very first safe design criteria curve. Basically, anything above their line was the danger zone. This was an absolute game changer. It gave engineers their first real, math-based tool to figure out if a pipe was susceptible to acoustic vibration.
But, as we know, engineering is always evolving. F.L. Eisinger came along and gave Carucci and Mueller's work a crucial upgrade. Instead of just looking at the overall diameter, Eisinger plotted acoustic power against the pipe's D/T ratio. That's the diameter compared to the wall thickness. By factoring in exactly how thick that metal was, engineers got a much more accurate picture of how sound frequencies were lining up with the pipe's structural frequencies to literally tear it apart.
Section 4. The Energy Institute Guidelines Framework. The modern methodology.
While those early pioneers laid the groundwork, modern industry needed something way more comprehensive. See, offshore plants started pushing for higher flow rates, removing bottlenecks to increase capacity, while simultaneously using thinner, more flexible pipes to save on weight. Because of that, the risk of fatigue failures just skyrocketed. So the industry built a robust new methodology, which became the modern Energy Institute Guidelines. It's a rigid, 3-stage playbook. Step 1 is a qualitative assessment to spot the excitation mechanisms and rank the risks. Step 2 is the qualitative assessment, crunching the heavy mass to find the exact likelihood of failure, or LOF. And Step 3, corrective actions, applying practical solutions to drag that risk back down to a safe level.
Section 5. Case study, system failure, and a real-world investigation.
Let's actually see this framework in action. Imagine a failing system with 2 pressure-reducing valves, or PRVs, just vibrating violently from sudden pressure drops and super high gas velocities. Engineers took this whole system and modeled it using CSRI software to hunt down the exact failure nodes and stress points. They calculated the sound power using those original Carucci and Mueller formulas to check the limits. And boom, the software showed the system was specifically failing at the small bore connections and directly at those 2 PRVs. They essentially pinpointed the exact hideout of the invisible killer.
Section 6. Applying the fixes and engineering disaster averted.
Armed with those quantitative likelihood of failure scores, it's time to actually fix it. The Energy Institute guidelines give you a pretty fantastic toolkit of corrective actions here. You could mechanically stiffen things up by tightening clearances on your supports. You could manipulate the flow itself, reduce fluid velocity, lower the mass flow rate, or apply flow smoothing. If that doesn't work, swap the hardware, change the valve type entirely, or just change its internal trim. Or you could literally just absorb the energy by slapping on viscous dampers, shock arresters, thickening the pipe wall, or adding specialized acoustic silencers. It's a really comprehensive arsenal.
And here is the mathematical proof that this whole framework actually works. Look at the likelihood of failure, or LOF. Before the countermeasures, both of those PRVs had an LOF well above 1.0. In this framework, anything over 1 means that pipe is in active danger of tearing apart. Not good. But after applying the targeted fixes we just talked about, those LOF scores absolutely plummeted down into the safe zones, hitting anywhere from 0.63 to 0.92. The dangerous vibrations were entirely neutralized.
So what does this all mean? The big takeaway from this explainer is the sheer value of this modern vibration analysis. Diagnosing AIV and FIV using these exact Energy Institute guidelines is literally what keeps our global infrastructure running. By hunting down these failure points early and calculating the likelihood of failure, we stop catastrophic plant shutdowns, we save millions of dollars in ruined equipment, and most importantly, we ensure absolute safety for the folks working around these massive, high-pressure systems.
But engineering never sits still, so it leaves us with a pretty fascinating question. As industries keep pushing the boundaries, demanding higher flow capacities, extreme pressures, and thinner, cheaper materials, will our current guidelines be enough? How are these frameworks going to have to evolve next so we can keep silencing the inevitable killers of the future? Definitely something to think about. Thanks for joining me on this explainer.